խոսեմ, որովհետև we are connected through Connect 2 to my TV station, which airs in Ամերիկայում, Կանադայում, Մեքսիկոյում եւ աշխարհով մեկ միացել ենք հիմա live եւ դրա համար ես ուզում եմ հեռուստադիտողները ինչ որ դիտում են իմանան մենք California State University Northridge-ում ենք եւ սա 16-րդ Science Olympiad-ն է, որը այս տարի ինչպես ամեն տարի տեղի ունենում։ Կարճ ամփոփ պետք է բացատրեմ հեռուստադիտողներին, երևի դուք այստեղ ներկաները բոլորը գիտեն արդեն, որ այս միության ղեկավարությունը սկսել է Science Olympiad-ը ավել շուտ, քան թե Los Angeles-ը։ Ուրեմն մենք պետք է շնորհակալ լինենք այս միության ղեկավարության այդ ժամանակ, որ խելացի էին կարողացան իմի բերել մի աշխատանք, որը շարունակվում է մինչև հիմա։ Ես Վրեժ Աղաջանյանն եմ, նախագահը Ամերիկահայ ինժեներների եւ գիտնականների միությանը եւ այս միությունը տարբեր բաժանմունքներ ունի, որոնցից մեկն է Science Olympiad, ինչպես ասացի 16-րդն այս տարի տեղի ունենում։ Եվ այս տարի շնորհակալություն Սվետլանա Արութունովային, Սոնա Ջոհարյանին, որը համանախագահներն են, քոչերներն են այս աշխատանքի, ինչ որ դուք բոլորդ եկել եք միացել եք։ Բոլոր մեր հեռուստադիտողներին, որ ծանոթ չեն, հայ ինժեներների եւ գիտնականների միությունը տարիներ 33 տարից ավել գոյություն ունի եւ մեծ աշխատանքներ է ծավալել։ Ամենավերջին աշխատանքը solar, այսպես energy վերաբերող կոնֆերանսներ ինչ որ տեղի ունեցավ Հայաստանում, որտեղ աշխատում են որպեսզի ծանոթացնեն եւ եթե կարելի է այնտեղ համասարանական մի ճյուղ, այսպես կարողանան ստեղծեն, որ ինժեներներ ունենան, սոլարին մասնագետներ կարողանան ունենան, իհարկե սա աշխատանքը նոր է տեղի ունենում։ Իսկ անցյալ տարիներում հազարավոր ծառ են տնկել երկար տարիներ առաջ եւ ուրիշ երկրաշարժի ժամանակ իրենց օգուտն են բերել, օգնությունն են բերել այս միությունը, այդ աշխատանքներին, ուրեմն այս ամփոփ այս միության կյանքն էր։ My name is Vrej Agijanian. I am the president of Armenian Engineers and Scientists of America. On behalf of AESA, I would like to welcome all of you to the 16th Science Olympiad in Cal State Northridge. I would like to thank committee co-chairs Svetlana Arutunova and Sona Joharian for their tireless effort in organizing this event. I also thank the judges, mentors, committee members, AESA members, students, parents, and Cal State University Northridge. I wish all participants good luck. And now, Sona will come and continue the program. I will be here at the side. I will do my own program, which, as I said, it's connected through the TV all over the world. They can see this, what you guys are doing in the past. Some of the viewers, they were aware of it, but they did not see what's going on in here. So hopefully this will give more, will bring more participants next year. Sona?
Good morning, everyone. Thank you for coming. We're really excited to see all of you here. My name is Sona Joharian. I'm one of the co-chairs. And here's Svetlana Arisunova. She's also the co-chair of 2016 and 2017 of Science Olympiad Committee. And I just wanted to wish you good luck. And I'll turn over the microphone to Svetlana, and she'll do her speech, basically.
Thank you, Sonajan. So exciting to be here today with you. Actually, this is very exciting turnout. As you notice, this location, this facility is different. We were exactly 1 year ago, actually, March 6th of 2016, we're meeting with many of you just across in Grand Salon. And today, we are grateful for CSUN to provide us with this facility with Armenian Student Association's help. And President of AESA was helping us to make this happen. We would like to thank Biaina. Where are you, Biaina? I don't see you. She probably left the room. Okay. So I would like to just say briefly what exactly was happening during this time since we met last at CSUN during the last Science Olympiad. So as many of you probably know, and most of you maybe don't, that after we had the event, which was very successful, and we had 105 projects last year, 130 students participated because it was group projects as well. And after the award ceremony happened and we knew our winners, we went and personally presented the monetary awards, the checks and certificates in most of the schools, the winners. And winners, the kids were taking pictures and school, and now they're nodding. The school is also proud of them, so that was in front of the whole school. So this way we are making sure that the school community, the students and teachers also are proud of their winners, of their teachers who are doing such a hard work helping them, and we really admire them for that. The other new things that were happening actually during this year, I forgot to mention that in terms of winners, we had last year several LA County winners and only one, California State Honorable Mention winner. So we would really hope that this year, with the help of your teachers, of the Armenian Engineers and Scientists of America, the community with the mentorship, that we could have, in terms of results, a little bit better outcome, that your participation would be hopefully resulting in a really high-quality projects, and the ones that would be winning the LA County Science and Engineering Fair would be selected for California State. And hopefully you guys would be one of those who would be winning, and we really hope that you succeed, and good luck to you in that regard. We believe that we can still do better in terms of number of winners in the LA County and California State, and that's why we would like to help as AESA Science Olympiad Committee. How can we help? Number one, mentoring. Whatever is going to happen today as a judging your projects, I would hope that you students would be considering as an opportunity to learn. Try to pay attention what kind of questions you are being asked, how exactly your thought process is in the presentation. So you will have an opportunity to practice your presentation skills. Try to learn from it and take it to the higher level when you are in next science fair. On whatever level. And there are so many different science fairs that we would like you to participate and succeed. How else we can help? We were inviting also organizations that we could collaborate with. We organized the workshop for our judges, mentors, and even science teachers, that we invited Wendy Hawkins from LA County Science Fair. And we also created a newly designed website that I would encourage you to please visit at aesa.org. That's where you were registering online. And I hope that you actually do explore and see that there are different categories, including for parents, for students, for judges and mentors, for teachers, so for the community, for sponsors that we do need, of course, and appreciate their financial support. And we hope that you actually go and explore the useful links that are there that are available for you. I'll try to wrap up so we can start the judging. I would like to inform you that this year we invite parents and public, our guests, to the public activity room, which is right on the right-hand side. The students would please take your stand next to your projects, and at 1 o'clock we would try to conclude the judging, and then it will be lunch, so you will be looking forward to your pizza, and then we're gonna have at 3 o'clock our wonderful keynote speakers, and actually the topic would be interesting today. So we have a STEM event. You know what STEM stands for, right? Science, technology, engineering, and math. And our topic, by the way, interestingly enough, is about STEM cells today. Okay, so, and then 4 o'clock is the award ceremony. So good luck. I welcome everybody. Thank you very much for being here. Sarkis, thank you. Sarkis wants to say a couple of words, please. Thank you.
May I have your attention? My name is Sarkis Barkudarian. I've been a member of this committee since its inception, even before, and I'm very pleased to see so many people participate in it. And I would like to tell you, as an engineer, we always count numbers. This project takes about 1,000 man-hours every year. And our goal, our dream is that, our members' dream is that we can be of help to the kids to improve their presentation and win first places wherever they go. So take the comments the judges make constructively, go improve, change your boards so you can win when you're going to LA County, LA City, or California. I just want to tell you that in the 16 years, we have awarded more than 200 talented Armenian kids. And we have given $40,000 in awards to these students. It takes a lot of time, a lot of energy, and anyone wants to help us in that area also, we'll be very glad. We have cards there for donation. If you want to talk to me, I'll be glad to talk to you. Your donation, one-time donation, is a permanent donation. We put it in an endowment, and we get the proceeds of it to be given for these awards there. And we also are supporting, we have an award for the best teacher of the year and the best school of the year. We give some awards there also. That's all. Thank you.
իմ անունս Վահան Որփերյանն է, 16 տարեկան եմ, 10-րդ դասարանի մեջ եմ եւ Rebbe Academy գուսանեմ։ Այս project-ը շինել ենք, որ Հայաստան ու Ադրբեջանը հիմա որ կոնֆլիկտ ունեն, այսի շինում է, որ Հայաստան, երբ որ ազերիները տեսնեն, ասի կարծում են, որ այսի հայկական սնայպեր է ու այսօր կրակեն, ոնց որ կրակեն հայաստանցիները տեսնեն են ազերիները ուր են եւ իրենց կկրակեն counter fire-ով ազերիներուն eliminate կանեն։ Այսի միտքիս եկավ մի հատ օրը թես ամալի ատեն Ղարաբաղ գնաց, ասեց որ հայերը արտին casualty ունեցան, որ ազերի սնայպերներով սոմդացեցին ինչ կնանկաներ այդ մասին եւ էսի սարքեցին։ Ուզում ենք որ այս ամառվա արդեն Ղարաբաղը ռքենք, թեստ անենք, եթե լավ աշխատում է եւ եթե լավ աշխատում է, ավելի մեծացնենք եւ mass produce անենք։
So that's your science teacher is John Shirajian?
John Shirajian.
Nice. So if English is better for you, explain how it works.
Okay, the way the circuit works is that it has 3 electrical components. It has a resistor, a diode, and a feedback amplifier. The way it works is that the feedback amplifier allows the circuit to operate at different voltage levels and regulates the brightness of the LED regardless of external temperatures such as external variance such as temperature or the amount of voltage going into the circuit. This gives us a significant advantage because it gives you a level of flexibility of the amount of voltage that's going into the circuit. The Estanka, we ordered it from online. Եվ սարքելը առանց instruction manual-ի եկել էր, սո միան նկարով նայելով պետք է սարքենք, եսի մի քիչ դժվար է, բայց գրծանք անել։ Եվ լրիվ բանը երբ որ շինենք, 6 անգամ պիտի լա այսօր չափը, եսի 1:6 ratio-ով սարքել ենք, եւ վրան ալ կամերայալ բիտնենք, որ գրնանք remotely առանց այդտեղ լալու գրնանք քշել, որ իմանում եք որ գերտագոր եւ վրանը solar panel ալ պիտի անցնենք, որ երբ որ օրվա մեջ charge անե, քիշերը էսի կորցած են։
Շատ հետաքրքիր ապրչատ օգտա։ Ինչ է LED-ին ինչ է անում? What's the reason for this? What you try to mimic?
We're trying to մենք փորձում ենք replicate անել սովետական երայից sniper, որ LED միան կորցածել ենք sniper ֆերից, որ punch չլա, dangerous չլա, LED կորցածել ենք, բայց լրիվ փանի մեջ infrared laser բիտնենք, որ էդի կորցածել են, սովետական ադենի մեջ infrared կորցածել են եւ էդի միմիկ ուզենք անել։
Ասենք որ ասում ավելի հին մոդելի, նոր մոդելի եւ հինի տարբերությունը ինչ է, որ ասենք նորերին վրա էլ ասի օգտագործեք։
Աչա դարբերություն չի կա, մի հատ ավելի գխելացան, ուր aim անում են, ավելի scope-ը մի քիչ mechanized.
The laser they produce is doing laser and
laser-ը նույն, էսի LED կորզածին, քանի որ LED ու laser-ը նույն internal structure ունեն, որ այդ որ այսօր վրա հիմա laser տնենք նույն ցևով աշխատում է։ Մի հատ difference-ը ան է, որ LED-ին լույսը disperse կլա, laser-ն մի հատ միտերի վրա։
Իսկ ինչքան կդստի laser-ով ասարքը, առանց
այս ամենը սարքելը, եթե ասենք մի հատ շինեցն է $500, բայց եթե 100 հատ շինես, նորեն $500 է։ Cost անը, որ այս circuit-ը print միտանես, մի հատ որ print անես, գնաց 1000 հատ order անել, ամեն մեկը 10 սանտիմից անել։ Main cost-ը անես սարքելը circuit board-ը, մի հատ որ սարքես, գնաց 1000 հատ order անել, ամեն մեկը 2 սանտիմ։
Բասպեր գինանեցա, որ նույնիսկ թանկն էլ չէ, εσύ կարող ես սարքել ուղղակի լեդես որոշ տեղեր գցես, ասակ իրենք աս լույսը արդեն Սորիան կարծեն թե որ բանում է։ Կարծեն որ սնայպեր գլա, սո էսի երկու կորձ անում է։ Մի հատ որ ազերներուն փամփուշները waste անում է, իրենք ափոլ կորսեցնում են։ Էս հայկական սնայպեր ցանկ կբահենք, մեր casualty չլա ու եւ ամենակարևորը իր սնայպերի տեղը գտեստաս։ Գրագել են իդ կարծեմ։
It reveals their location. Yeah, we can eliminate them through counter fire.
Nice. Very good. Thank you very much. Very good project. Very to the point. Շատ կարևոր ասում է։ Շատ արդիական է։ Շատ շնորհակալ։
Բարև, իմ անունս Կարոքելյանն է ու ես HBU MHS-ից եմ։ Ես այս project-ը մարել, որովհետև ուզում էի գտնել ավելի էժան բան, որովհետև սրանք շատ թանկ են։ I always
Okay, go to English, don't worry about it.
I always launch rockets. That's my hobby. I do that, and those are very expensive. And if you keep getting them all the time, it gets a lot. So I found a cheaper alternative, which were these, and this is $1 each for each one of these engines. And it's just a mixture of 100% potassium nitrate and sugar, and that's this mix right here. And there's this old dowel here. I use this as a template, and it helps me figure out how much to put and where to put it. And the white mix is what fuels the rocket motor. The bentonite clay I'll just use it as a barrier between the white mix and the delay mix. And the delay mix is just the white mix but with a little bit of baking soda. And the delay mix is used for the time delay so that whenever it's in the air and the white mix finishes, this burns a little bit slower, and then after this the parachute ejection charge goes off and the top pops off and the parachute comes out. Now, yeah.
Well, basically, have you done a comparison, this and that? How is it,
this one,
how far this flies?
This one goes 1,200 feet, and these ones go 1,600 to 700 feet.
So you basically improved it. This is reusable? You can reuse it?
No, it's not.
Disposable?
The inside melts and the clay stays there.
And the tube, you can reuse the tube?
You can.
Yeah?
Yeah. It's disposable.
Disposable. So this costs $1. This costs about $10.
That's $15 for that one pack. So it's at least $5 for that little one.
So you basically saved 5 times.
Yeah.
Which is pretty good. And then you improved the performance.
I did, yes.
Did you try to improve even further? Like try to get a much heavier rocket to fly, longer to fly?
I might in the future, yes, I will.
It will be very interesting if you could figure out the way that makes it better.
I can get maybe a longer and thicker pipe and make it bigger.
Better, maybe something else that can mix with it. So it could be very useful.
There is another thing that I can mix. I can mix the white mix with some rust, and that will make it burn. That will make the thrust increase. So if this is, let's say, 10 pounds of thrust, it'll be at least 15-16 pounds of thrust with the rust in it.
So I think this kind of rocket engine called a hybrid engine.
Yes.
So basically, this is the same engine that's used in the military, like when they shoot the rockets and things like that. It's the same kind of.
It's just a
so
minor scale version.
Well, exactly. If you can improve on that, it might have a good use in Armenia.
Yeah.
So that's this project, and this project is very interesting. Thank you very much. I appreciate your time.
My name is Armin Ghazarian, and I'm from St. Gregory Hovsepian School in Pasadena. My project is on the effects of heat on a graphics processing unit. Now, graphics processing unit is the part of your computer that displays an image on your screen. Now, when heat is generated in your graphics processing unit, it's because too much data is flowing through the graphics processing unit, which causes the transistors in the graphics card to start heating up. Now, in the graphics card's microprocessor, it tells itself to stop all the data flowing through it so it has a chance to cool down. Now, by changing the fan speed, I thought that the lower temperature would give the graphics card more headroom to pass more data through it. In this experiment, I changed the resolution from 720p to 1080p to 4K. Now, these are all standards for consumer tech that uses screens. I changed the fan speed using a program that precisely changes the percentage of the fan speed running on the graphics card. I chose 25%, which is the lowest. Then I went to 40%, 50%, and 60%. I ran a benchmarking software that consistently runs the exact same thing every single time. It's called Unigen Valley, and the camera goes through a valley at the exact same rate, speed, and everything is exactly the same every single experiment. So everything in this experiment but my independent variables are the same. Now, during this experiment, there are different areas that cause different increases or decreases in FPS. FPS is frames per second. It's how fast your screen refreshes. Now, going through some parts of the camera, it went through places where it just showed dirt on a hillside, to places where there was sun shining on your screen, snow, rain, and fog all at the same time, which are very graphic intensive parts in that video, which meant that my FPS will go down. Now, by increasing the fan speed, there obviously in resolutions there are different, there are more or less pixels on your screen. Now, 1280 by 720 has less pixels than, let's say, 1080p, which is 920 by 1080. Now, in order to get the total number of pixels running, you have to multiply these two numbers. Now, the more pixels there are on your screen, the more the graphics card has to work in order to generate every single color in that pixel. Now, basically, in short point, my hypothesis was correct, and that when you do increase the fan speed, which lowers the temperature, the FPS or frames per second goes higher.
Did you find out any point of diminishing returns? Basically, you get to the point where you're increasing more and more, the speed doesn't make sense.
One thing I ran into, which is also part of collecting data, is when we went to 50%, it just shot up, and we couldn't figure out why. So obviously, that's part of collecting data. So I included it to show that's what happened.
But did you find out what rate it doesn't make any? And then that's very important to present in your presentation, because that's what we're trying to find out. What it was, because at some point we get to the speed that no matter how much we increase the speed, it doesn't matter.
100% is the maximum speed, which is 4,500 RPM fan speed, and that is the maximum that the graphics card can reach. So if you look at the graphs, because we kept everything constant, the graphs look very similar. Now that just shows that when you increase it, it's increasing at the same rate. So let's say if we did do 70%, I would be able to determine, let's say on an average, where that temperature or FPS will be.
And what does this graph show here and here?
It's the temperature, and then the temperature going this way, which is going up, and then the FPS, which is going higher. So basically what it's showing is the lowest temperature is the highest FPS. Then it goes and it's starting to decrease a little bit. Once we got to 60 degrees, that's when it went all the way down to 60 FPS. Yes.
Good job. Thank you very much.
Thank you.
I'm from St. Gregory Secondary School. My project is on the acceleration of the eggplant plane. The materials I used were 3 feet of molding, a 12-inch roller, a stopwatch, an eraser used as the end point for the golf ball, a protractor to measure the debris angle, a stack of books, 16 for the 25, 10 for the 20, and 7 for the 15, a golf ball, and a marker to mark the places at 20, 40, 60, and 80 centimeters. So first, I marked the points 20, 40, 60, and 80 centimeters on the molding. Then, using the protractor and the books, I measured how much the debris angle was for each of the debris angles seen here, and stacked as many books I needed so I could get an accurate a golf ball and a stopwatch. I rolled down the golf ball and timed how long it took to go down each of the points from the start to the end. My results were either that they were similar to each other or they were the same. For example, the 20 centimeter one for the 25 and the 20-degree angle were 0.16 seconds to 0.18 seconds. My hypothesis for this project was if I roll down a golf ball from the molding at different heights, then the golf ball will go faster on higher degree angles and slower on lower degree angles. My independent variables were the golf ball and the molding, and my dependent variables were the 25, 20, and 15 degree angle, the speed of the golf ball, the time traveled by the golf ball, and the books. In conclusion, the higher inclined plane is, the faster an object will move down from it, and the lower an inclined plane is, the slower object will move down from it.
What grade are you in?
7th grade.
So you take physics already? You have physics classes or not yet?
No, not yet.
Not yet. So when you take the physics classes, make sure you come back to this experiment and try to formulate it. Find the formulas why it's happening. Then that will be a very interesting project. You can add the formulas and then basically explain with physical terms and mathematical terms why this is happening. It's a very cool project.
To add on to this, Galileo performed this project himself first, but instead of using a stopwatch, he used a mechanism using water that dripped every second, which was his stopwatch basically. Any questions at all?
And where did the Galileo do that experiment? Did you know?
No, I don't know where he did it, but I know how he did it.
Do you know the Pisa in Italy when they have the leaning Pisa, the building that leans a little bit? They used that building to do the experiment. Since it was already lean, they could measure it. Thank you, very cool project.
Her PhD research is focused on the investigation of electronic cigarette exhaled residue. She plans to identify the components of the residue as well as its toxic effects on different cell types. Now I would like to give the floor to Karine. Please welcome her.
Thank you so much, Sona. Okay, guys, before I give a talk, I want to tell you that I will be talking today about stem cells. So, hopefully there are some biologists in the audience. Okay. So again, Sona mentioned that my name is Karine Khachaturian. I am a graduate student receiving my PhD at the University of California, Riverside. If any of you students have any questions about PhD, masters, you can always come talk to me afterwards. Hopefully it's a goal for you guys. If not, maybe you want to just ask me questions you're interested, you can go ahead and ask me. So in this presentation, we're going to learn about stem cells and regenerative medicine. The purpose of this presentation is not to tell you what to believe about stem cell research. I want to just lay out some facts and give you some biology. So, moving forward. So let's start with the basics. What is stem cell research and what is the purpose of studying stem cells? Well, stem cell research helps us understand more about development, aging, and disease. To do this work, scientists have created experimental model systems which resemble normal processes in order to learn more about the process of growth in early life or the degeneration of tissues later on in life. By using these experimental model systems, scientists can also understand how genetic mutations or specific chemical messages lead to disrupted stem cell functions in various diseases. And then finally, these discoveries can be applied to direct stem cells to do things that will help patients, which is basically the ultimate goal of regenerative medicine. And then in this regard, stem cell research may help us prevent or treat diseases and injuries in two ways. The first one is cell-based therapies and pharmaceutical development, which includes drug testing and drug delivery. So let's go through a few examples of these different cell model systems and their therapies. Okay, so I'm gonna play a movie for you and I'm gonna talk through the movie. Here we go. Another way we can use stem cells is to grow them into replacement organs. In 2008, doctors grew a replacement trachea for a woman whose trachea had collapsed as a result of tuberculosis. So what they went ahead and did is they used a cadaver and they took the trachea from the cadaver, so they cut it out, which you can see here. And then what they are going to do is now wash away all of the cells from the cadaver so that there's nothing left, it's just the bone. And they will take a stem cell from the woman who had the tuberculosis, and they will actually grow her own cells. So here you see one cell turning into two, turning into hundreds, thousands of cells. What they'll do is they'll actually repopulate the trachea with all of her own cells. And then what they're gonna do is now they're gonna cut the trachea again to fit it correctly to her own trachea. And then they will cut out her injured trachea, which you will see here. And they'll go ahead and replace her injured trachea with this brand new trachea with her own cells. And the purpose of this was that they actually didn't have to do any chemotherapy to kill her own cells to fight this new trachea, right? Or the new cells that come with the trachea. So that's a good thing about stem cells, because these cells came from her own body. So, outline of this presentation. The first thing I'm going to talk about is an introduction of fertilization and embryonic development, because that's where this whole stem cell talk begins. And then, so let's go ahead. So, conception in a dish. This is a picture of multiple male gametes digesting the outer shell of the egg in a race for the center. So here are the male gametes, and here is the egg. Notice what a big difference the female gamete has in size compared to the male gametes. And male gametes use enzymes in their head, and after they get to the egg nucleus, the egg prevents any more male gametes from entering. Okay? And there's something called in vitro fertilization, which is the male and the female gametes interact in a dish. They literally swim up to the egg and burrow towards the nucleus. And the first one to get there wins, right? So here's an example of intracytoplasmic injection. It places a male gamete right inside the female gamete's nucleus, so there's a better chance of a fetus being produced. And here's how this procedure works. After stimulation using hormones, between 10 and 30 female gametes are removed from the woman's ovaries. Male gametes are collected, and one male gamete is sucked up into this little tube. On the left, we have a holding pipette, this is the pipette here, which secures the female gamete in place. And again, you see how much bigger the female gamete is compared to this little male gamete right here. And what's amazing is that they both contribute the same amount of genetic material to the developing organism. So next we have the male gamete containing the man's half of the genetic contribution, which is then injected into the female gamete containing the woman's half of the genes. And this is the day 1 of fertilization. At 12 hours after fertilization, you can see the 2 bundles of genetic material. These contain the DNA from each parent. By 18 to 20 hours after fertilization, these bundles fuse and combine genetic material from mom and dad. What starts out as 2 cells becomes 1 cell called the fertilized egg. So now we're at day 2. That 1 cell is now divided into 2 cells. How do you guys think these cells are related? Can anyone tell me? No? No one? Huh? Yes? I can't hear you. They're identical, exactly. You're exactly right. So later on in day 2, each of these 2 cells divides, making 4 identical cells again. By day 3, each of those 4 cells divides, making 8 identical cells. Each cell is now 1/8 the size of the original fertilized egg. Now, some fertility doctors choose to put the embryos back into the uterus at this stage, and some wait until the embryo is more developed. On day 4, the cells have divided several times now, and you can't tell one cell from another cell. So how do you think these cells relate to each other? They're again still identical, correct? So now day 5 is a huge day. Now fluid builds up inside the ball of the cells, making it look hollow, kind of like a soccer ball. This structure is called a blastocyst. Cells are identical at this point. The outer layer has cells that will become the placenta. There is a clump of cells sitting inside, and there you go, those are, that will become the fetus. However, this is definitely not a fetus yet. So now the doctor chooses a few, usually 2 to 3 healthy looking 5-day-old blastocysts, and he implants those inside of the woman. Hopefully, one, and preferably only one, of those will successfully develop into a pregnancy. Embryonic stem cells make up the little clump inside of this blastocyst, right here. Okay, so at what point is this a fetus? So remember, natural fertilization happens in the fallopian tubes, and it takes 7 to 14 days for the developing embryo to float down to the uterus and implant. When the embryo implants, the clump now looks like a disc. There are 3 distinct layers of cells, an outer, middle, and inner layer. Cells in these layers don't look like mature organs and structures yet, but based on their position, they will eventually become specific layers. So I want to ask the group, what parts of the body do you think this outer layer will form? Yeah. Yes, exactly. Smart kid. This layer forms skin and, interestingly, also the nervous system. So what do you think the middle layer will form? It will become the muscles, bones, and heart, exactly. And what will the inner layer form? Yeah? It will actually form the gut lining and internal organs. So the brain will come from the, we'll see later on, but from the middle layer. After this, the nervous system begins to form. The cells in here become the spinal cord and brain. Bumps begin to develop near the head end, and this will be the future face, neck, and mouth and nose. In the next 5 weeks, parts of the embryo will become specialized into primitive organ systems. The primitive heart starts beating in week 4. By week 8, what do we have? Fetus, exactly. Remember, embryonic stem cells used for research are harvested from 5 to 14-day old embryos, way before organ formation starts. The donors always have to give their permission to use embryos for research. So here's another kind of cool video that I'm going to play for you. This is going to be a video of the development of fish embryo. This would help you visualize how an embryo develops, because every vertebrate or animal with a spine pretty much starts out like this. This movie begins with the fish having 64 cells. It proceeds very much like human embryonic development. And then I want to mention, on the left, we see one side of the embryo. This is a view of the animal pole, which is the side of the embryo that is actively dividing cells. On the right is the opposite side of the embryo, also known as the vegetal pole, which has the yolk cells that divide less rapidly and give nutrients to the cells of the embryo. So I'm going to go ahead and play this. So on the left, you can see cells rapidly dividing or proliferating. You can see cells migrating around the embryo to form a hollow ball. Then the clump of cells of embryonic stem cells forms at the future dorsal side of the embryo. So right here, your back. The clump reshapes and starts to form the spinal cord and future brain. So here you can see a future brain starting to form. You can see that the brain is now starting to look heart-shaped with the beginnings of two hemispheres, right? Because your brain has two hemispheres. And on the right is the beginnings of a segmented spinal cord. So you can already see here the brain, and then this would be the spine. And this is how you developed as well. Okay, so what makes stem cells unique? At the beginning of embryonic development, stem cells undergo what's called symmetric cell division. They divide symmetrically when one cell splits, right here, and gives rise to two identical cells that have the same potential. This is why we said the stem cells in the early embryo remain the same and are identical. This is also how fully mature cells in your body divide. So, then at blastocyst formation, remember it was those little cells inside of the embryo, and gastrulation, the stem cells start to divide asymmetrically. When these stem cells divide, they give rise to two cells that are different from each other. One of the cells remains a stem cell, right here in yellow, and then the other changes into what's called a progenitor cell, the green square. That progenitor cell is a young cell that will change into a mature cell type like the epithelial cell in green. And asymmetric cell division is when a stem cell divides to produce two cells that are different from each other. One of the cells remains a stem cell, demonstrating self-renewal, and the other differentiates into a progenitor cell. So now, okay, so that the stem cell has now divided to produce a green progenitor cell, which differentiates into a green skin cell. That stem cell can divide again, this time producing a different type of progenitor cell, which matures into yet another cell type, so something like the brain cell. So can you guys tell me what makes a stem cell unique? Right here? Right. Exactly. And it can self-renew. And also it has a capacity to give rise to different progenitors that change into mature cell. Okay? So this is an example of producing a neuron. So this is actually pretty interesting. What do stem cells look like? I never knew this when I was in middle school and high school, so it's great to see these kinds of pictures. There are actually thousands of human embryonic stem cells growing in this circular colony. The human embryonic stem cells are grown on top of a mouse feeder cell, these longer cells right here, which provide essential nutrients. And some of the essential nutrients that the mouse feeder cells provide is like an extracellular matrix for these human embryonic stem cells to live. So here's another microscopy image. Scientists can label embryonic stem cells using these glowing molecules. Maybe you've heard of them, such as GFP or M-cherry. On the left, the smaller blue dots inside the green label the nuclei of the embryonic stem cells, and the blue dots outside the colony label feeder cells. So this one is like a zoomed out picture, and then here when we zoom into these stem cells, you can see about 15 to 20 embryonic stem cell colonies. Embryonic stem cells like to grow in little colonies spaced out over the dish instead of one big layer, like other cell types. Okay, so what are the different types of stem cells? So this is a diagram that'll eventually, show the entire range of development from fertilized egg to mature cell type in the body. And then, so again, we see this, the 8-cell stage, which is known as a totipotent stem cells. And these stem cells can become any single cell type in your body. They have a lot of power. And this doesn't work. Okay, so they're also known as totipotent cells. And this cell can form the embryo and the placenta. But if we move forward to this blastocyst stage, remember we talked about specifically these cells inside of the blastocyst. These can form the embryo, but they can no longer form the placenta. And those are known as pluripotent stem cells. So then what we can go ahead and do is we can harvest these cells and we can culture them and make them into any cell type that we want. So moving forward from there, then we can also obtain adult stem cells or tissue-specific stem cells that have restricted lineages. So they can no longer become any single cell type in your body. So you've already grown and you're making these cells in your body. And these are called multipotent stem cells because they will only become mature cells from the tissues in which they live in. Adult stem cells are present throughout your entire life and replace fully mature yet damaged and dying cells. So don't worry guys, you still have adult stem cells that you can use, and they could, so an example are blood cells, nervous system cells, and connective tissue. So adult stem cells in the brain. Adult stem cells are found all over the body, and here's a few examples. Who here has been told that your brain cells can never regenerate? Have any of your teachers told you that? My teacher has. Well, in this case, it's actually not true. Relatively recently, scientists discovered that two specific parts of your brain, neural stem cells, divide and differentiate to become neurons and glial cells. Without neural stem cells in the hippocampus, you probably could not be able to learn or remember anything. And then here in this top right picture is a cross-section of a rat hippocampus, which is part of your brain. And neural stem cells are in the blue right here, and these little tiny blue dots are the neural stem cells, which divide and differentiate to form mature neurons, which are the green cells here. And then we also have astrocytes. It's another type of cell in your brain here in the red. And then here in this bottom picture, we have cultured neural stem cells. So these are no longer in your body. This is a scientist took out these neural stem cells and decided to culture them. And you can see the neural stem cells are these plain blue dots. And derived from those stem cells, then you have neurons, which are these blue dots surrounded by the red. And then you also have something known as oligodendrocytes, these blue dots surrounded by the green. So, in the skeletal muscle, stem cells are activated immediately after an injury to help replace damaged muscle. So imagine the muscle fibers running down Arnold's bicep. They're kind of like a bundle of spaghetti, right? So we are going to take a cross section of that muscle. So you have all this spaghetti, and we're gonna break that so we can get a cross section. You can see all the muscle fibers. Okay, so that's the cross section, and here's an image. Okay, can anyone tell me where the stem cells are in this picture? It's kind of tricky. Yes? Where are the stem cells in this entire picture? It's kind of difficult. So it's actually these little pink dots right here, okay? So the tiny pink dots eventually turn into the green cells, which add together to form the red muscle fibers. So when Arnold lifts weights, his muscle stem cells proliferate and differentiate into new muscle fibers, which add on to the existing fibers to increase the size of his muscles. This is part of the reason why muscles get bigger with exercise. And by the way, this is not actually Arnold's bicep cross-section. This is actually a mouse muscle. Okay, so how do these stem cells know what to become? Cells stick and respond to molecules embedded in their extracellular environment. So right here. They also respond to chemicals or molecules floating around in the liquid surrounding them. And cells can also feel and communicate with each other and also can respond to forces. So you guys can tell me, how might an embryonic stem cell respond if it touches a bunch of muscle cells? Yes? Exactly. It might differentiate into a muscle fiber. And how do you think that same stem cell would respond to culture with a bunch of neurons? Yes, it'll turn into a neuron. So here, this stem cell is going to make a decision to self-renew or differentiate based on the individual components and combination of these factors in the extracellular environment. Sorry, I just want to explain one more thing. So this stem cell can self-renew or it can differentiate. It has a choice to make. So how do these cells know what to become? All cells in a person share the same genetic code. Given that their DNA sequences are the same, why are your eye cells different from your nose cells? And if you cut your hand, let's say, how do your cells know to make more skin cells or endothelial cells, epithelial cells? Well, it's actually dependent on the environment outside of the cells, also called the niche. And that niche influences the switching on and off of different genes. The change in gene expression alters the physical characteristics of the cells. And I'm sure you guys have already seen this. It's called the central dogma of biology. You have DNA, turns into RNA, turns into protein, and it gives you a specific cell type. And then we can use these cells for tissue therapy. So this is an important part, guys. So if growth factors and hormones affect stem cell function, then our lifestyles, our experiences, and our behaviors are also likely to influence stem cell-related processes. For example, regular cell growth in blood and skin, wound healing throughout the body, and other types of processes. So not surprisingly, what is good for your body is good for your stem cells. And so what's good for your stem cells is also good for your body. Because the regulation of stem cells not only plays a really important role in various disease states, but also proliferative cells actively participating in maintaining overall cell health. So make sure you guys have low stress, regular exercise, enriching experiences, learning new information, and healthy diets rich in antioxidants. Okay, and then so I wanted to show you guys some examples of stem cell research, therapies, and technologies now that we know where stem cells come from and how they develop. And let's talk about what's going on right now in stem cell therapy. Okay, so these cells are heart muscle cells. They were derived from mouse embryonic stem cells, and they beat spontaneously in the petri dish. So I'm gonna play this. The ones on the left have one epicenter of beating. Okay, and then the ones on the right have 3 epicenters, which is the center where it actually beats. These are experimental model systems that give scientists a way to study how the heart works. Scientists can also genetically manipulate these cells so that it might have a better understanding of defects in disease. And one thing I'm sure you guys have already learned about is bone marrow transplant, and this is actually done with adult stem cells. Although they're a little bit harder to obtain in pure form than embryonic stem cells, adult stem cells do have therapeutic potential. Okay? So what happens in bone marrow transplant? Basically, a donor's tissue type is matched with the patient's tissue to make sure the patient won't reject the transplant. This is really important to understand. Tissue types always have the potential for immune rejection if you don't carefully match the donor. Next, bone marrow containing human hematopoietic stem cells, which are your blood cells, is taken from the donor's pelvis. So here you can see this is the healthy donor and this is the patient. And what happens is that the cells are extracted, and this is the unfiltered marrow, but then what needs to happen is that they need to filter it to get pure marrow. And then what happens is that they actually have this sick patient who has the unhealthy blood cells. They need to perform chemotherapy on her to get rid of the malignant blood cells. And what happens is there's an IV transplant so that this healthy marrow is injected into the patient, which will then hopefully the patient will become healthy. Okay. Another video I wanted to show that has sound, and hopefully I think it works. Okay, so one way that we can use embryonic stem cells is to kind of coax or encourage them to differentiate into progenitor cells for a certain type of tissue, such as nervous. And those progenitor cells have a healing effect when transplanted. I'm going to show you a video from a Bay Area biotech company. Their name is Geron, and they were sponsoring the first FDA-approved human embryonic stem cell trial to try to bridge the gap from research to therapeutics. So let's check out the video.
This animation illustrates the results we obtained when we tested.
Does it not have sound, guys? But you can hear it from mine. You can't hear. Let's see if this works. Okay, I'll try to hold it.
This animation illustrates the results we
Better?
obtained when we tested glial cells derived from human embryonic stem cells in a rat model of spinal cord injury. The actual animal data, graphically represented here, were published in the Journal of Neuroscience in May of 2005. Under anesthesia, animals are given a permanent spinal cord lesion, which causes them to lose control of their hind limbs, trunk muscles, and tail. This weakness is due to the surgical lesion placed under anesthesia in the thoracic portion of the animal's spinal cord, resembling an acute human spinal cord contusion injury. The injury is severe and permanent, and as we look closely within the animal's damaged spinal cord, we can visualize the mechanism of the animal's loss of motor control. Transmission of nerve impulses pass along nerve fibers insulated with myelin, a protein which is made by the glial cells shown here in gray. When the injury occurs, the glial cells die and the myelin insulation is lost, which stops the transmission of nerve impulses at the site of the injury. Our glial cell therapy involves the injection directly into the injured site of new glial progenitor cells made from human embryonic stem cells. The injected cells then turn into mature glial cells that actually replace the myelin insulation, thereby restoring impulse transmission along the nerves. This results in restoration of spinal cord nerve transmission, which leads to durable improvement in the animal's hind limb control, trunk muscle strength, and tail control.
So I thought this was a pretty cool video. You can see that the mouse had an injury and you injected embryonic stem cells, which turned into neurons, and then you have, you allowed the rat to replace its glial cells. Okay, so that way embryonic stem cells were coaxed or encouraged to differentiate into adult stem cells, progenitor cells, or fully mature cells. So I want to talk about putting this all together. So why are people so interested in using human embryonic stem cells? Why not just use adult stem cells or something called induced pluripotent stem cells for research and therapies? Well, embryonic stem cells are pluripotent, and their expanded development potential allows us to study development and model diseases in a way that we could never do with adult stem cells, because remember that adult stem cells only become specific cell types. Embryonic stem cells can proliferate or divide symmetrically forever, and some people call them immortal cells. Adult stem cells stop proliferating after a certain number of cell divisions. And embryonic stem cells are fairly easy to obtain, and this is also why some people do not want to use human embryonic stem cells. There is kind of like an ethical issue with that as well. But however, this remains to be seen. So new scientific disciplines like stem cell research are all about posing questions and finding answers to life's mysteries. We have already learned a lot in the years we've been doing human embryonic stem cell research and in the years before doing adult stem cell research. The knowledge we have now, including the information in this presentation, is subject to change. Everything changes in science every single day. And so because of scientific inquiry and the need for more advanced medical technology, we can always ask questions about stem cells and see where stem cells take us. So hopefully this has encouraged the future biologists in our group to look into stem cells or any other cell type. Do you guys have any questions for me about stem cells or about biology? No? Okay. One more thing I'd like to mention is that I did graduate from CSUN as an undergraduate, and I went to UCR not knowing that I wanted to be a PhD student. I always thought I was just going to get my master's and work at a biotech company, but I was kind of encouraged to obtain my PhD and move on further in my biology career. And one thing I would like to recommend to all the kids here is that don't only stick to one subject, do as many subjects as you can. So if you're a chemist, learn biology, learn engineering, learn physics. If you're a biologist, learn physics, learn engineering, learn everything you can, because when you move on into a biotech industry, public industry, they want you to know as much as possible, and it'll look very good on your resume. So I always thought I was just going to be a biologist. I ended up learning some engineering, software engineering. I deal with chromatography, mass spec, so I'm a chemist, I'm also a toxicologist. So please don't limit yourself to one thing. You will be surprised as to how much you can learn. And I'm gonna give the floor to Sarkis now. He's a physicist. Sona? Sona? Is Sona here?
Okay, go ahead.
Ura bana. Evet, kortika.
Pointer.
Չէ, որ kortika ուզում էր։
Ձերսակականս։
Okay.
Հետո որ պետք է
All right. Now we're going to have Sarkis Barkhudarian, who's a former AESA president. He was a past president of AESA in 1994, and he's been one of the first members of AESA Science Olympiad when it was established in 2001. Sarkis Barkhudarian has obtained his master's degree in electrical engineering from Carnegie Mellon University. He's been a chief for technical fellow of Boeing and developed advanced technologies for rocket engines. He's been awarded for 20 plus patents and has been publishing 20 plus publications, and has been managing 30 scientists, over 30 scientists. And now please give the floor to Sarkis Barkhudarian.
Thank you. Okay, since AESA has awards for biologists as well as the physicists, Corinne covered the biology part, and I'm going to be covering the non-biology part, the physics part of it. I was working at Rocketdyne over here, very close, and I was developing technologies for rocket engines. And 9 of my technologies are deployed. So you guys can also get that happen to you too. Okay, I'm going to be talking about spectrometers. And you say, what does spectrometer have to do with rocket engines? Well, I asked an old friend of mine to send me one from Florida, and this is a spectrometer. Let's see, this is the spectrometer that I'm pointing to you. And this is a rocket engine of the space shuttle. The shuttle has 3 engines at the end of the wings. There are three round engines that you see, and they are like that big rocket engine. The diameter is 8 foot, and it generates 500,000 pounds of thrust. And it runs for only 60 seconds. And when a plume comes out of the rocket engine, it has colors based on what is burning inside. If everything is normal, the colors won't be changed. But if, let's say, copper is burning or chromium is burning, you see different colors in the plume, and that will be bad news. So now I want to talk to you about fiber optic spectrometer and I need somebody to pass this around. This is my kid's toy there. These are fiber optics, and there's only one of this in a cable that will go around. So if you look at the spectrometer cutaway, light comes from here and reflects from the mirror and gets diffracted like a rainbow, and you see different colors. These are actually visible colors, by the way. And they're recorded on, they're detected on this sensor that provides you the signal that we can benefit from it. This spectrometer monitors from 300 to 800 nanometers and has a resolution of 0.3 nanometers. That's how we measure how sensitive it is, how small an impurity we can detect in the plume. And as you can see, it's very small and very lightweight. Okay, let me see which chart we're talking about. All right, we had to develop a special cable, a fiber optic cable like this, having one of the fibers from that toy there inside it, 120 foot long. And it went from the tip of the nozzle that you saw all the way to the engine, and it had to withstand very nasty environment of the rocket engine. It is about 8 feet, and that little white probe was sitting here, and the temperature coming out of plume was 6,000 Fahrenheit. But the nozzle itself was chilled with liquid hydrogen, and that was like minus 420 Fahrenheit. So the probe had to withstand cold temperatures and hot temperatures same time. I have to tell you this, NASA tried it, they put a big contraption there, they put a lens and everything else there. When the engine fired, the probe broke off and fell down, almost blew up the rocket engine. But our design, this one, had no components in it. It was completely blank, and it survived. The cable carried the signal, and it had the optics on the receiving side. So that was quite a surprise, successful surprise. And a vibration, the worst vibration on any rocket engine or turbine engine is right on this nozzle, and that's where we had to have the probe survive. Install and survive, right here. Okay. All right, and we took that spectrometer that went around, and it was designed for laboratory usage, so we had to ruggedize it to put on the engine body. So we, believe it or not, ruggedized it with Teflon caulking material, and it survived. And this is a typical clean engine spectra. You see the wavelengths here, you see the time, like 1 to 50 milliseconds, and this is the intensity of the signal in some arbitrary units. And the benefits of the spectrometer was to detect what is eroding inside the engine, because like ball bearings are rotating or valves are moving, and sometimes they erode, and often we get the whole engine blow up. Actually, before the rocket engine, the shuttle rocket engine was approved, I went back and forth, yeah, sorry. We blew up like 49 engines, each one of them about $50 million. But that's how we learned to design it and make it work, and they never failed on the shuttle program. Okay, now the next chart. All right, then we were trying to see how correct we are, and nobody believed in us, the old-timers especially. They said, no way you can measure anything there. So we had to run a test to prove that we can detect. We took the inside the nozzle, This is the edge of the nozzle, and you're inside the nozzle. And we painted it, pasted it, some powders of ink alloy, which has chromium, nickel, and iron in it. We just pasted it there. And the total amount of the powder was only 50 grams. And they ran the engine. And we were monitoring the plume, and we were able to see these traces of the nickel, chromium, and iron as a function of time now. So the engine starts here. For a while, nothing happens. This is when the flame is dancing around. And then things got burning and getting high temperature. And you see the alloy is burning. And then it does a funny thing. They call it burping. And it will burp again and again. The spike will come again. And this is the level of nickel and iron and chromium when everything was settled down. So by this time, all this paste was burnt out. Okay, they said, okay, can you test better than 50 grams? Maybe we want to measure less of it. So we went down there to only 0.6 gram of that powder was in that paste. And we pasted, and we again showed that we can detect all the 3 alloys in that Inconel. And that was, of course, the numbers are smaller, but it's still quite a nice contrast between what we call signal to noise. All right, so that's the end of my presentation. And if you have any questions? The spectrometer is worth $2,000. And thank you. The spectrometer is only $2,000, but the cable took us maybe $50,000, $100,000 to develop and build and fabricate and install. And that space project, they all are very costly. Okay, questions? Yes? Lady in red. Who has the probe, the white probe? Who has the white probe? Who has the white probe?
Thank you.
Oh, okay. Can you bring the white probe and give it to Svetlana? The lady in red is Svetlana. You see that white thing? That was the probe that we installed. And the one that NASA installed was this long. They put a lens in front to collect more light. They thought the more light you have, the better off you are. They didn't think that you will have the sensitivity. And there's nothing in it except the housing that the cable threads onto it, and the 2 bolts are to attach that to the nozzle walls there. Yes.
Okay. And what is this material it's made of?
This was Inconel, one piece, but this is a 3D piece of the probe.
Inconel?
Yes.
What's Inconel?
It has the nickel, chromium, and iron in it. It's an alloy, very high temperature alloy that can withstand 6,000 Fahrenheit.
Interesting.
But this one is made out of plastic, right? This is a 3D sample.
Probably. You know better. I don't know what it's made
okay.
of. That's what I'm asking. Interesting.
Yeah, the Inconel will be much heavier.
Oh, I see.
It's a metal used in rocket engine hardware because it withstands higher temperature, vibration. It's a tougher baby. Any other questions? Yes. Okay.
Working. What do you gain from this information in terms of preventative action?
Very good question. So the question is, okay, you're running the engine and 7 astronauts are on an orbiter, and you suddenly detect this unusual, erroneous, abnormal amount of, let's say, Inconel in it. What will you do? Okay, you would inform the office in Houston, say, we saw this much of this Inconel. And then the next question for the people in Houston to decide to shut it off, that engine, or keep it running, is to know where that hardware is eroding, which one of the 4 turbines and all that. If they could have done that, then they could have said, okay, we think that this turbopump cannot withstand the remaining of the flight, shut it up. If they think it's all right, they would have flown it, continue flying it, yes. The shuttle was designed to run even with one engine working in a nice place, far away. So if you lost one engine out of 3, you still could have made your mission. If you lost 2, you could have made it depending where you are in your orbit. Good question. We call that health management system. And where's Razmik? He will love that. Okay. Any other nice questions?
I will take one last question and start with the award announcement soon.
Oh, the lady in red has another question. Give her the...
So, for example, if right now there is some tool that is being designed and developed, let's say NASA JPL, and they want to test it right now for the vibration and how it's gonna not fail or not break apart and actually get to the mission safely, because when it gets to the destination, it would need to make sure that it's functional, it's, you know, the way it was designed and supposed to be functioning. So what is the actual thing to consider and to go about, to think about, that it would not break, that it would be safely, you know, getting to the destination?
Okay, that's a very, very nice question. And very complex.
Sorry, yeah, it is complex.
And there are a lot of things you have to do. When the engine flies, 2 things are really bad news. One of them is excessive vibration. If a turbine decides to vibrate too much because it's not balanced and all that, if it blows up, all the propellant comes out and a fire starts and the engine burns, and if the engine burns, the whole shuttle will burn. So we call that criticality 1. So to prevent that, we monitor every 20 milliseconds these 100 parameters of the rocket engine. And based on that, we make a decision to continue flight or not. So you put something like this, it will be before the vibration sensors, the accelerometers will show any high amplitude, and it will tell you something is eroding. And then the next thing is the accelerometers will come in and say, oh, we're seeing some vibration on turbine number 2, for example. And the guys down in Houston, they'll say, okay, how much of vibration is this? How many more seconds we got to go? And then they'll make a decision to shut it off or not. So it's a preventive measure, as the gentleman alluded. Good question. Any other nice question? One thing I can tell you, yes, that this plume spectrometry is similar to when you accidentally pour salt on your burners at home. You see the yellow light. This is what we call optical spectrometry spectra. You will see that. Yes. We got to talk louder and stand up, please.
Will the space shuttle burn if it's in space?
I didn't hear the question, sorry.
Will the space shuttle burn if it's in space?
Did you hear what she said? Oh, what's the fuel? Very good, very good. What's the fuel of the rocket engine? Liquid hydrogen and liquid oxygen. And we don't have that on the ground. It's very, very dynamic, powerful, but it's also very dangerous to have it there. It's just almost tinderbox. We call that controlled explosion when the engine gets fired. Yeah, you can hear it. They used to fire them in Santa Susana, and people could hear it in the city, and they couldn't sleep. So they complained, so they decided not to fire during nighttime. Fire only during daytime. That was a nice question. Any other question? Yes. Needs a speaker here, please.
No more questions, please. No more questions.
Okay, all right, okay. All right, yes.
What's the highest heat the probe can withstand? The probe.
Highest
The highest temperature
that can
the probe can withstand?
the engine can withstand?
Yeah.
Believe it or not much, only 1800 degrees Fahrenheit. But what we do when we want to go to 6,000, we pass liquid hydrogen in the back and we cool the place there so they will not see 6,000 degrees. Good question. Very good. Thank you.
All right. Thank you, Sarkis. Okay, so we're coming close to our end, but I would like to just tell you a little bit about AESA and AESA Science Olympiad. AESA was established 33 years ago on June 30, 1983, with an objective of creating venues for all engineers, scientists, and industrialists of Armenian descent so they might network, interact, and help one another. We as the AESA know that our community future depends on the next generation of engineers and scientists. We have about 8 committee organizations, and one of them is Science Olympiad, which was established in 2001, and the first Science Olympiad was done on February 2002. Our goal is to increase interest in sciences and engineering among young Armenian students such as you, and foster your knowledge beyond the confines of a classroom, provide recognition of outstanding achievements you've done, and also by the teachers. So now that you're going to become a doctor, scientist, and engineers, right? After this Science Olympiad that you've completed? Where's the enthusiasm? All right. That's what I was hoping for. Okay, so now that you're going to become doctors, I hope you don't forget to come back and join AESA. Especially, we have created a new organization, young professionals, you in mind. With that said, I would like to thank the schools that are participating this year. Can I get a shout out for AGBU Manukyan Demirjan School? Holy Martyrs Farahian School? Vahan and Anu Shamlian Armenian Schools? Armenian Mesropian School? Alfred and Margaret Hovsepian School? Charlotte and Ellis Merdinian Armenian Evangelical School? I love the enthusiasm, by the way. Sahak Mesrop Armenian School? AGBU Vache and Tamar Manukyan High School, Pasadena? And finally, Ribe Academy. All right. I would like to also thank our volunteers and committee members for their hard work in organizing this event. A special thanks to our judges for taking their time out of their busy schedule on a weekend to be here with us. And also the exhibitors who were here to show you some interesting projects they're working on and producing. Last but not least, I would like to thank our sponsors and donors and get the award and invite them over the stage with Svetlana Artunova so we can start passing the awards. So which group do you guys want to start with? Junior physicals? No? Okay, junior life science? How about senior physical science? No? Senior life science? No? I think the winner is junior life sciences, so we're gonna go with that. Donors or sponsors, please come up the stage if you haven't yet. Sponsor چه بازگنه؟ School.
You're going to give the name, and I will be doing the medal?
Do you want to switch back and forth? No?
Just do this. I wouldn't shake hands with the kids. Like last time, I didn't do that.
Okay. Do you want me to just read their names? All of them? Yeah. Okay, that's fine. I can do that. Baskin. While we're getting ready here, I would like to mention that we're taking a group picture towards the end, so do not leave once we're done. We have to have a very nice group picture because last year we missed it. Okay, with that said, junior life sciences. Dr. Shahen Khanjarian Honorable Mention Award goes to Eric Markarian from Shamyan Armenian School.
And let me congratulate you too. Very good job. Thank you. Good job.
No, so don't they stay on the stage?
Yes, just stay on the
Amalia Gubrekan Honorable Mention goes to Natalia Opel from Merdinian Armenian School.
I saw. That's fine. Yeah, because it looks like you are a strong girl, right? But congratulations. Okay, yeah, there is. We have to put. Okay, then let me go this way. Okay,
Svetlana Minasyan third place award goes to Eric Harutunian from AGBU Manukyan Demircan School. And it looks like he's probably gone for games, so unfortunately we'll give it to their teacher to pass it to Eric. Barkhudayan second place award goes to Sofia Seradian from Merdinian School. And she's not here either. Okay. Mr. and Mrs. Zaven and Sonia Akyan, first place goes to Darun Yakubian from Gregorian Hovsepian School. Okay, I guess you... Okay, he's at a soccer game, but his teacher is receiving his award. Okay, next up is Junior Physical Sciences. There's a lot of nervousing going on here. So, Nazari and Grigor families honorable mention award goes to Derek Tomasian and Andrew. Ask them right now. We don't have their school. No, just us.
So you want to mention that? So
Which school are you? Okay, they're from Shamlian School, by the way. We just There's two. Oh. Միատ եք փոխ էլի, բանը փոխ բավելի։ Հա, մեդալը միատ փոխեք։ Հետև մի հատ կարակ եթե մցնեք, լավ կլինի։ How are we doing so far? There is no need to be stressed because you all did a great job. If you're here, then you did a great job being here. Okay, next is Kalayan Honorable Mention that goes to Ani Karajayan from Merdinyan Armenian School. Keeps on falling.
And I have to mention.
No, don't say that. Like something like.
And I have to mention that we were actually judging. The AESA 4 judges came to Merdinian School, and actually that was the moment when I did see this student, and I was very impressed. And I'm glad actually that she won. And of course, I'm excited and proud about every one of you here. But that's the interesting that we do see how you guys grow and perfect your projects. That's wonderful. Thank you.
Next is Besdikian Family Honorable Mention Award goes to Tadet Perumyan from Shamlian Armenian School. Dr. Vrejuhi Daryan Honorable Mention Award goes to Anthony Tokatlian from Merdinian Armenian School.
Congratulations. Good job.
Manatoyan Honorable Mention Award. Wow, we have a lot of honor awards. This is another honorable. Okay. Rafael Manaskanyan and Atoyan Honorable Award goes to Mary Uygan from Ribe Academy.
Very nice. Good job. Congratulations.
Eddie Atoyan, third place award goes to Robert Dergarabetian from Merdinian School. Alex Grigorian, Second place award goes to Aram Petrosyan from Ribe Academy. Second. He is very excited to get his award. Gubrekan family first place award goes to Armen Ghazarian from Hovsepian School. Congratulations to our junior life sciences and physical sciences winners. They did a great job. Again, all of you did a great job, but they were recognized for their even harder work. Next, I'm going to present the senior life sciences projects. Mr. Simon Gubrekan, in memory of George Gubrekan, Honorable Mention Award goes to Stephanie Khachikyan from Vacha and Tamar Manukyan School, AGBU. Dr. and Mrs. Alexander Grigorian third place award goes to Galin Akhyan from AGBU Vacha and Tamar Manukyan School. Okay. It's your turn. Dr. Emmanuel Aaron Shirajian, first place award goes to Sarah Aintablian from AGBU Vache. Congratulations. Next, we're going to senior physical sciences. We're going to start with the third place. Agbabian and Grigor families' third place award goes to Vahan Vorperian from Ribe Academy. Congratulations.